I am Anish Chandran, Assistant Professor, Computer Science Department, Jyoti Engineering College, Cheruduruthi.
Hello all. In this session, I am going to discuss about the topic paging. Okay, in the previous session, we discussed about segmentation. In segmentation, we will divide the primary memory into a large block of segments and of various size. And in this paging technique, we will divide the primary memory as well as the logical memory into equal size memory blocks, that is memory chunks with same size. And in logical memory it is called as pages, and in physical memory it is called as frames. And we will map these pages into frames which is in the physical memory. So the main problem with the segmentation is the external fragmentation problem. And by using this paging technique, we can avoid this external fragmentation. Okay. And also avoid problem of varied sized memory chunks, because here we will divide the primary memory into equal number of fixed sized blocks called frames. Okay. Then the size is of power of 2. And between 512 bytes and 16 megabytes, that is frame size and also page size. So here the main thing is that we need to keep a data structure which is called as page table to translate this logical to physical addresses. Because the CPU, each and every time the CPU will generate a logical address, and we need to map that logical address with the physical address. So for that purpose, we are using this page table. Okay, then the thing is that keep track of all free frames. So we need to keep track of all free frames which are available in the primary memory. And keep in mind that the physical address space of a process can be non-contiguous. That is the advantage of using this paging technique. That means we can copy each and every pages into frames which are available in the primary memory, which may be non-contiguous. That's the advantage. So process is allocated physical memory whenever the letter is available. Okay, here also then we have a small problem called internal fragmentation. So now we are going to discuss about the address translation scheme. Here the CPU will generate a address which contains two portions, that is a page number P used as an index into a page table which contains base address of each page in physical memory, and also a page offset combined with the base address to define the physical memory address that is sent to the memory unit. The thing is that the CPU will generate the address of a single location in the physical memory. So we need to map that address into the exact location in the physical memory where the data resides. So for that purpose, this address is divided into two. That is, first we will get the frame number, base address of the frame, and from that we will add this offset to get the exact location in that particular frame. Okay. Here is a picture. The P is equal to M. P will be the size of the P will be M minus N, and the offset or displacement D will be N. For given logical address space 2 raised to M and page size 2 raised to N. So the page size will be 2 raised to N and the address space will be 2 raised to N. We will discuss it with an example. So here is the paging hardware. Here we can see the CPU will generate an address with page number and a displacement. The page number will give the corresponding base address of the particular frame, and from that frame number, from that location we will receive the frame base address, and we will add this displacement with this frame number to get exact location. Here it is the frame of size something, and in this frame we will access, or the CPU will access this location. Now This is the meaning of this address calculation. So here we are using a data structure called page table, and we will map the corresponding address in the physical memory. So how can we map this logical memory to the physical memory? Here we can see that in logical memory there is page 0, page 1, page 2 and page 3. That is 4 pages are there. And here is a page table. For page 0 the frame number is 1. Page 1 the frame number is 4. Page 2 the frame number is 3. And for page 3 frame number is 7. So we can see from here that for page 0 it is actually mapped into frame number 1. For page 1 it is actually mapped to frame 4. Likewise for page 2 it is mapped to page 2, and for 3 it is mapped to page 7. So from here we can clearly understand the use of these page table data structure. And also keep in mind that this is a data structure, so it will also reside in the same physical memory. Here is another example. For example, if n is equal to 2, that is displacement is equal to 2, and m is equal to 4, that is 32 byte memory and 4 byte pages, which means here we can see that 1, 2, 3, 4 byte pages are there, and total 4 into 8, 32 byte memory will be there. Okay, here for each pages there we can store 4 bytes of data. 1, 2, 3, 4. Here for each pages we can store 4 bytes of data, and this entire page will be mapped into a frame in the primary memory. You can see that this entire page is going to map to the primary memory, and the CPU will generate a location in this frame. For example, if CPU needs to use the data B, then it will generate address 1, and the operating system will map that address that contains some page number. Page number here will be 0, and it will be mapped to the frame number 5, and here we can see that 0, 1, 2, 3, 4, 5, and in 5 we will map it into the first one, that is displacement will be 1. So we will the CPU will get the data B. Okay, here we can see that page 0 is mapped to 5, that is 20 to 24, that is we can just multiply with 4, because 4 bytes for each and every frames. So first 4 bytes for page 0, and the second 4 bytes for page 1 likewise. So frame 1 likewise. So 0 page is mapped to frame 5. So here ABCD is here, and then first frame is mapped to 6. So EFGH will be there, and second frame page is mapped to 1. That is this one is mapped to IJK to this second frame. First frame. 0th frame is this, and first frame, and the third page is mapped to 2, that is MNOP will be there. This is the 0th frame, this is the first frame, and this is second frame. So 3 is mapped to 2. Okay. Now it is clear that how can we map these pages into frames. Here calculating internal fragmentation is an example. If suppose the page size is of 2048 bytes and process size is equal to 72766 bytes, then we need 35 pages plus additional 1086 bytes for occupying this process. So here the internal fragmentation will be 2048 minus 1048. That is 2048 is the page size minus we need 1086. That is 35 pages plus 36th page. We need only 1086 bytes. So we will subtract this 1086 from 2048, which will give the internal fragmentation. So the size of the internal fragmentation will be 962 bytes. The worst case fragmentation is equal to 1 frame minus 1 byte. That means if there is 2048 bytes in a page and we are using only 1 byte, that will be the worst case of fragmentation. On an average of fragmentation is equal to 1 by 2 frame size. That is half the frame size. So small frame sizes is desirable. That is a question, but there are lots of problems, because when we are using frames with smaller sizes, then the size of the page table will be increased, and the reference time will be also increased, which will cause which will affect the efficiency of the system. But each page table entry takes memory to track. That's a problem. Page sizes growing over time. Solaris support two page sizes 8 KB and 4 MB. That is, the page sizes may be different in different operating systems. Okay, then there is another picture. We can see that the free frames. We will keep track of the free frames which are available in the primary memory. Here we can see that 14, 13, 18, 20 and 15 are the free frame list. And new process page 0, 1, 2, 3 are there. And we will map these page 0 to the first free frame 14, second to the 13. That is 13 is now free available. Then 2 to the 18. Because here the free list 14, 13, 18, 20 and 15 are there. So 0 will be mapped to 14, first one. And 1 will be mapped to 13, 2 will be mapped to 18, and 3 will be mapped to 20. So we can allocate like this. That is, the system will keep track of the free frame list, and whenever a new process needs to execute, then it will be loaded into the corresponding frames which are free in the free frame list. Okay, then how can we implement the page table? Page table is kept in main memory. Keep in mind that page table is kept in main memory. So it is a data structure. Page table base register is used to point to the page table. For each and every page table, there will be page table base register. Page table length register indicates size of the page table. It is the same as the segmentation. In this scheme, every data or instruction access requires two memory accesses, because the page table itself in the primary memory. So we need to access the page table, and the next access will be for the corresponding data. The two memory access problem can be solved by use of a special fast lookup hardware cache called associative memory or translation look-aside buffer. TLB is an important topic, which is actually a high-speed memory element like cache, and the hardware is here. From the hardware, we can see that there is a TLB. So whenever CPU requests for a data, it will first look it in the TLB. That is, a portion of the page table will be copied into the TLB with respect to some criteria like temporal locality or spatial locality. And if the corresponding entry is in the page, in the TLB, then it is a TLB hit, and the corresponding frame number will be there in the TLB itself. So the CPU never needs to look into the page table. That is, the double reference we can avoid. And if it is a TLB miss, that is, it is only a portion of the page table, and sometimes it may be a TLB miss, and that means the corresponding entry will not be in the TLB. So during that time only, the system needs to access the corresponding page table. Okay, then the same thing is happening in both these memory elements, but the advantage is that it is a high-speed memory element compared to the primary memory. So whenever a TLB hit is there, and it will happen in very short time. And another case is that memory protection, because we are using page frames, and it is not for each and every process we are not copying the entire process in a same memory area. That is, it is not contiguous. So we need to provide some protection mechanisms. One is that valid or invalid bit attached to each entry in the page table. Valid indicates that the associated page is in the process logical address space and is thus a legal page. And if it is a valid bit, that means it is a single binary bit. And if it is one or if it is valid, it indicates that that page is the process can access the corresponding page. And if it is invalid, that process cannot access that page because it is not in the corresponding logical address space of that particular process. Or use page table length register, which will give the length of the page table and avoid the violation of accessing. Avoid the problem of accessing unauthorized pages. Any violations result in a trap to the kernel. That is, it will be an error. Valid or invalid bit, we can see from here that for page 0, corresponding frame number is 2 and it is a valid bit, so that particular process can access that frame. And here we can see that for page 6 it is invalid, so we cannot access, or that particular process cannot access that page or frame in the primary memory. Here, okay, the next case is shared pages. We can see that there will be shared code. That is one copy of read-only, re-entrant code shared among processes. That is possible because read-only pages we can share among processes. And similar to multiple threads sharing the same process space, also useful for inter-process communication if sharing of read-write pages is allowed. That is, only for read-only code we can share these codes among the processes or data in the process. Private code and data. Each process keeps a separate copy of the code and data. The pages for the private code and data can appear anywhere in the logical address space. Here is an example. Here we can see that ED1, ED2, ED3 are shared pages, and here we can see that 3, 4, 6, 3, 4, 6 and 3, 4, 6 both are ED1, ED2, ED3 are mapped to these 3, 4 and 6. So these three processes can access these 3, 4, 6 frames in the primary memory. That is the session about paging. Okay, see you later. Bye.